Imagine that you're in the last 50 meters of a 400-meter race or a 200-meter swimming race or something like that, or you're playing in your hockey match and you've had to make repeated runs to get forward, to get back, to attack, to defend. It's a big match, you're under pressure. That feeling in your legs, or it could be other parts of your body, that heaviness, that pain, that lactic acid buildup, what is going on there? How does that actually happen? What causes that? And let's see if we can understand it. So, we're going to start a bit of a journey here, folks. And we're going to start with an old friend of ours. We're going to start with glycogen. And glycogen is effectively our stored carbohydrate. And I want to remind you that glycogen is stored in the muscle tissue itself and in the liver. Remember that the liver is the bigger store, but nevertheless, we've got glycogen in our cells, in the tissue that's going to produce that muscular contractile force. Now, that glycogen is going to be worked on. And it's going to be worked on in a process called anaerobic glycolysis. Lysis basically means to cut or to break down. So glycogen is going to be cut, it's going to be broken, and we are going to produce something which you guys will have a solid awareness of is glucose, but we're going to refer to it as glucose 6-phosphate. Now, I'm not going to get into the importance of the nomenclature here. I just want you to sort of accept that from me, that we now have this glucose 6-phosphate. And this is quite a complex reaction, this glycolysis, by the way. And there are enzymes involved in that. For example, we have an enzyme which is called glucose phosphorylase. Okay, we can refer to it as GPP. That's one of many enzymes involved in this process. But this process itself actually consumes 2 ATP. So it takes 2 ATP to do this, actually to follow this process. But we're going to take this further. We're going to take that glucose and we're going to break that glucose and we are going to convert it into something called pyruvic acid. Now, this pyruvic acid can now go in one of two directions. It can be processed aerobically, and you might want to imagine that we've got an aerobic pathway here. But in our example, we have insufficient oxygen to follow the aerobic pathway. So what are we going to do with this? Oh, sorry, I should have said this breakdown here is done in the presence of something called PFK. Now, I'm sorry, this is a ridiculously named enzyme. I'll write it over here for you. It's called phosphofructokinase. Nothing I can do to make that word short, I'm afraid. There's an O here. Phosphofructokinase, PFK. Now, this pyruvic acid, in the conversion of this, that was meant to be yellow, in the conversion of this pyruvic acid into lactic acid, we are able to release 4 ATP. Okay, or resynthesize, you should say. So in that context, we have got a net plus 2 ATP for our system here. But this lactic acid, which by the way has been worked on by another enzyme called LDH, and I'll write that up here, lactate dehydrogenase, hard to say that and write it at the same time, lactate dehydrogenase. This lactic acid now forms a fatiguing byproduct in the muscle tissue and in the blood. Okay, so what we've done here is, yes, we've managed to release a net gain of 2 ATP. We've managed to do it from glycogen, which is broken down to glucose into pyruvic acid, the present of these enzymes in, by the way, the sarcoplasm of the muscle cell, or indeed the cytoplasm of any other cell. But we're able to do this, but we have this fatiguing byproduct of lactic acid. Now, before we go on to the analysis of this, I just want to stress that lactic acid doesn't remain lactic acid very long. It actually breaks down into lactate, which is actually quite a useful product. We can use it for energy, and we can restore it, do various things with that. We can convert it to urea, all kinds of things. But it also releases hydrogen ions, and it's those hydrogen ions that will go on. What will happen with here is this will actually denature or change shape of other enzymes in the environment and mean that other, for example, aerobic respiration process can't take place. So, what's our analysis? Let's go through this. What is the type of reaction? Well, we have not got the presence of oxygen here, or sufficient oxygen, so it's an anaerobic reaction. what is the fuel? The fuel right at the start was glycogen. Okay, we had a glycogen molecule either from the muscle or from the liver. What was the site of reaction? This happened in the sarcoplasm. So once again, a little bit like, well, once again, depends what order you're watching these tutorials. Like the phosphagen system, we have got sarcoplasm as a site of reaction. Our active enzyme, the one you're going to use is PFK. This is an active enzyme. You can also use GPP, glucose phosphorylase. The enzyme you shouldn't write down as your active enzyme is lactate dehydrogenase, LDH. That is not active in the energy release part of this process. We also get a yield of 1 glycogen to 2 net ATP, so a yield of 1 to 2. We can also say that the byproducts, and of course in this case fatigue in byproducts, yes, we have got lactic acid, which again, as I mentioned before, breaks down into hydrogen ions and lactate. In terms of our intensity, we would describe the intensity of this system as high, not very high, but high intensity. And finally, before we do the evaluation, what about our duration of this system? Well, this system will endure up to 120 seconds, 3 minutes, but it will often be shorter than that if it's a more intense physical activity. Now then, we always follow this process. We always want to do our evaluation of this system. So what are the advantages, the positives of this system? What's good about it? Well, first of all reactants are in the cell. They're ready. So therefore, we've got no, because this is obviously anaerobic, we've got no oxygen delay. No delivery of oxygen needs to be made for this system. And furthermore, this system can fuel high intensity energy. Fantastic, we love that. Now, there's a little bit of a negative and a trade-off, right? So our disadvantages are fairly clear of this system. So I wonder if you can sort of figure out what these are. Well, I'm going to tell you that we've got a low energy yield. Now, obviously, this is more yielding than the phosphagen system, which is 1-to-1. We get 2 ATP for each glycogen here, but we have got a low energy yield that's still inefficient compared to the aerobic system. We have got a short duration. Now, again, it's longer than the phosphagen system, but it's still short duration. But perhaps most importantly, we've got fatiguing byproducts. And I just want to bring you back to your GCSE biology days, folks, where you will have looked at the influence of both temperature but also pH levels on the activities of enzymes. Now, of course, if we've got lots of hydrogen ions that are making our blood sort of like lower pH, more acidic, then of course what's going to happen is that other enzymes in the environment, let's say that all of our aerobic enzymes, let's say lipase, for example, which is all about the breakdown of fats, aerobic enzymes cannot fulfill their role. These enzymes are denatured. That means they change their shape site, and their binding site becomes non-available. Go back to your lock and key theory from GCSE. And as a result of that, we get a sort of a rapid sort of loss of energy release, and therefore we fatigue very quickly afterwards. So we'll look at lactate inflection point in another tutorial. But it's quite interesting with lactic acid. It can kind of build up gradually in your bloodstream, but once you hit a certain point, it rapidly increases. Okay, and this is called obla. We'll come back to it in another tutorial. Cheers.